Hello, we're back to the Introduction to Differential Equations, Chapter 9, and we're going to go over some modeling of real-world applications. And so you'll see where differential equations can come up. All right, so first let's recall from algebra the statement that if some object is proportional to x, then we can translate that to say, if y is proportional to x, that y is some constant times x. Good. So we'll use that, and we also recognize that whenever we discuss a rate of change, rates in general, comparison of two quantities with different units of measurement is usually a rate, but our rate of change is a derivative. So let's take a look at this first example. Write a differential equation described by the following description. Note that all rates given are with respect to time. And part A says the number of bacteria present in a petri dish grows at a rate proportional to its size. So first we have to introduce some letters or some variables. So let's just say let B equal the number of bacteria at time t. Then we can say, if we take a derivative, the derivative of b with respect to t is going to be the rate of change of bacteria in the dish. Good. So if we were to write the statement, the number of bacteria present in a petri dish grows at a rate proportional to its size. So the rate is proportional to its size. So if I'm going to translate that, I'm going to say dB dt is a constant times its size, and the size is the number of bacteria at time t. Good. So there you have a differential equation in B. All right, this is similar. Hydrocodone bipartrate is used as a cough suppressant. After the drug is fully absorbed, the quantity of the drug in the body decreases at a rate proportional to the amount left in the body. So again, we need to introduce some letters. So let's say let H equal the amount of the hydrocodone bipartrate. So the amount of in the body at time t. So if it's a function of time, so you're looking at h of t. So again, the rate of change is dH dt is the rate at which the drug is in the body. And taking the statement, the quantity in the bug decreases at a rate proportional to the amount left in the body, or the amount in the body, then we can say here that dH dt is proportional equals a constant times the amount that's left in the body. But I want to point out we're saying decreases, so you might want to add a negative sign here to make sure that your rate of change is negative. Because if you've got a rate of change that is negative, you know your original function is decreasing according to that first derivative test. So we want to highlight that, and you can say where k is bigger than 0, right? So then you have that negative. All right. Another example. A turkey is taken out of the oven and placed into a room of 80 degrees Fahrenheit. The temperature cools at a rate, sorry about that, proportional to the difference between its temperature and the temperature of the room. So rate is proportional to the difference between its temperature and the surrounding temperature. Those of you who are familiar with this might be familiar with Newton's law of cooling. So we, again, if we want to use, let T equal the temperature of the turkey at time t, then we know that dt little t is going to be its cooling rate, right? Or the rate that the temperature cools. So looking at rate is proportional to the difference between, so rate is, so if I do dt and I have an equal, proportional to is going to be your K, and the difference between its temperature and the temperature of the room is what you're multiplying K by. So we would have dt is equal to K times the temperature at time t minus the temperature of the room, and the temperature of the room is 80. Good. And that is a differential equation. All right. A fish population in a freshwater man-made pond grows at a rate inversely proportional to the square root of the population present. So if you say y is inversely proportional to x, that translates to y is equal to k, but the inverse makes you want to take the reciprocal of x. So here, let's call big F the population of fish at time t. So df dt is going to be the rate the fish population changes. And the inverse proportion, it says the rate is inversely proportional to, so our df dt is going to equal a constant, that's our proportional constant, and we want to take the reciprocal of what? The square root of the population present. Good. So you can translate that from its sentence to mathematical symbols. All right. Perhaps in a pre-calculus course, you worked with the exponential growth and decay model, and that is this one here. And now, because of your knowledge of separable differential equations and using the fact that the law of exponential growth or decay states that a quantity grows or decays at a rate proportional to its size. So if we let y equal to be the size of the population at time t, then dy dt is going to equal a constant times y. And k is known as the growth rate. And you could use this for decay rates as well. So in looking at the solution to the differential equation, we go ahead and separate our variables. We take the derivative of both sides, getting to the equation of ln of y equal to kt plus c. We then exponentiate both sides so that we solve for y. And then we use our exponent rules to separate e to the kt plus c to make it e to the kt times e to the c. And then we use the e to the c as our new arbitrary constant, right? Our e to the c would be our arbitrary constant here. And then we would use, and so then we get to our y equal to c times e to the kt. Now usually we will have an initial value. So at the beginning of a problem, you might know we start off with a particular population. So at time t equal to 0, we would have y of 0 would be the initial population, right, at time t equal to 0. And if we use our general solution, this is our general solution, and our initial values here, so when t is equal to 0, y is equal to y sub 0, the initial population. If we plug that into our general solution, then we have y of 0 is going to equal c times e to the k times 0, and e to the 0 is 1, and we know that that output should be our initial population. So we then conclude that y of 0 is equal to c. And therefore, we end up with our general model for exponential growth and decay of y of t is equal to the initial population times e to the kt, and k is what's known as your growth or decay rate. This is, of course, if you've got a population that is allowed to grow with endless resources and perfect environment. There are, in future sections, discussions of the logistical model of growth and decay, which takes into account limiting factors such as food and environment. All right. So we, it shows our exponential models of growth and decay. And I'm going to stop here and go on to more separable differential equations. I just wanted to derive that classic exponential growth and decay model. And you can try this one on your own. And I will see you guys in the next video.